Hi, I'm Tommy Thompson, and this is AI in Games, a series on research and applications of artificial intelligence in video games. We're back in the Mushroom Kingdom to take a look at academic research in Super Mario Bros. Nintendo's ever-enduring franchise has cropped up a couple of times on this channel, having looked at both the Mario AI competition that ran at academic conferences between 2009 and 2012, as well as how AI researchers have sought to better encapsulate and model Mario level design for procedural generation purposes. In this video, we're catching up with some of the new and ongoing research in applying machine learning to Super Mario level generation. I'll be looking at the kinds of levels they're generating, how these algorithms go about building a Mario level, and the opportunities that still lie ahead for this research field. It's time to meet the new Super Mario makers. Before we look at the varying projects and systems in earnest, let's cover some basic theory of what I'm talking about and the big changes that have happened in the field in recent years. If we cast our minds back to the original Mario AI video I posted in 2014, I explained how the Mario AI competition introduced several strands of research involving everyone's favourite plumber. While some of the challenges set by the competition, such as writing bots, were overcome pretty quickly, courtesy of Robin Baumgarten's A-star player, the challenge of procedurally generating Mario levels was only just getting started. The competition tasked researchers to not just create a system that made levels inspired by Super Mario Bros., but also attempt to customize them based on some simple telemetry data about the user that was playing the game. The resulting systems over the next couple of years were pretty diverse, both in terms of how they operated and the subsequent levels they created. While this video is focused on more recent work replicating Mario level design, if you're interested in learning about the more formative research in player-driven PCG for Mario, I'd highly recommend exploring work by Dr. Noor Shaker. But looking at more contemporary research, one of the largest transitions is moving away from building levels that adopt player telemetry, but instead seeking to mimic the original designs from Mario titles. What prevented this from occurring up until now was that these earlier research projects all embed their own design knowledge about what a Super Mario level actually is. Now, this is an interesting area of study all in itself. What makes a platforming level a Super Mario level? It's something scholars have engaged with in recent years to better understand the nuance required of Mario level generators. See, the thing is that while there are certainly aspects of the overall aesthetic that influence the process, what is more critical is the logic and structure to the layout of even the simplest Mario levels. If you give someone a piece of paper and a pencil and ask them to sketch you a Super Mario level, they'd probably differ in many respects due to that person's knowledge of the franchise, but there would no doubt be some common elements. There'd be brick blocks, maybe even question blocks, pipes, Goombas, Koopa Troopas. There might even be a pit to fall into and die, or a stairwell that would head towards the flag at the end of the level. We have a collective understanding of these core elements, but often lack the intimate knowledge of how these things should link together and the relationships between them that make the Super Mario series a continually fun and engaging franchise. Heck, Nintendo is so confident in their mastery of this concept, they've developed not one but two editions of Super Mario Maker, where they give you a fairly flexible tool for building your own Mario levels to play on a Nintendo device without any real concern of whether it would impact the sales of the main series.
Do it yourselves then, you think you're so bloody smart.
So bringing this back on point, Super Mario level generation research has continued to thrive. However, the biggest shift in recent years is the efforts to understand Super Mario level design. To address this, more recent work avoids having researchers directly inject their own interpretations of Mario level design, given, as mentioned, there is no absolute and complete set of rules that dictate how Mario levels are built that we can lift from. Even when given the tools to do so in Mario Maker, we ourselves not only struggle to reproduce the Mario method, but we often do something else entirely, a point that I'll come back to later. Now, the most recent research using machine learning has sidestepped this issue by letting the algorithms study levels themselves. As we'll see in some of the projects I'm about to explore, in each case the system is fed Super Mario levels to allow it to build its own internal models. The manner in which this data is fed ranges from annotations of design patterns to tile grids, reading in level graphics, all the way to watching YouTube videos. In each case, the system infers its own logic of how tiles should be grouped together, what tiles are used in certain contexts, and in some instances what texture should be applied to those tiles themselves. The process is enabled for these recent level generation systems to more accurately interpret and reproduce aspects of Super Mario level design. But enough of my babbling, let's take a look. So I'm going to explore 4 notable bodies of research in recent years, and while this is far from exhaustive, it gives you an idea of the sorts of avenues researchers are taking and the progress that's being made. Bear with me, as the range of AI methods and techniques employed here is pretty diverse. I do my best to quickly summarise what each system is doing and why it makes sense to go about it in this manner. For those of you interested to learn more, I've listed all of the relevant research papers in the video description for you to peruse in your own time. First up, let's take a look at the work of Dr. Steve Dahlskog, a lecturer at the University of Malmö in Sweden. Steve's work sought to assess Super Mario games using design patterns, identifying common elements in the layout or structure of levels or mechanics in games. His argument being that by establishing rules of how game elements are constructed, AI systems could adopt that knowledge as means to make intelligent decisions on how to make new levels or even games. This research has led to him exploring procedural generation of dungeon levels as well as player experience evaluation systems, but much of his research, particularly in the early years of his PhD, revolved around Super Mario Bros. Dahlskog's research starts in 2012 under the supervision of Julian Togelius by identifying 23 unique design patterns within 20 land-based levels from the original Super Mario Bros., omitting underwater levels and those in castles. These patterns range from micro-level behaviour, such as chains of Goombas or gaps presented in the level, to macro behaviour where level construction is more abstract, such as multiple paths or stairways constructed using pipes with gaps in between. If you want to learn more about this research, check out my second video on Mario from back in 2015, where we discovered that not only do these design patterns hold ground in subsequent sequels, but they're the crux of how many entries in the series innovate on Mario level design. Using these patterns as means to identify properties that would reflect real game levels, Dahlskog's second phase of research, published in 2013, employed evolutionary computation to build levels and then assess them based on the number of patterns found in each example. This is achieved by breaking levels up into 200 vertical slices, and then examining how those slices connect to one another and what patterns exist within subsets of those slices. The resulting output generates levels that reflect some of the classic Mario design patterns, but failed to respect the pacing of these patterns to create a more natural flow. This was followed in 2014 with 2 projects. One that rebuilt the level evaluation to record micro and meso level patterns distinct from one another, resulting in increased level variety, followed by a new level generation process, the multi-level level generator, that built levels at varying levels of abstraction, starting at macro pattern level, then working down to meso and micro. His final body of research in this space was published in 2014 with assistance from Dr. Mark Nelson, and while it's not machine learning, it's worth checking out, given it calculates continuing subsequences or n-grams of vertical slices in order to construct a Markov model of the level creation process. Markov models are a smart approach towards this, given they're designed to predict the subsequent action made in a decision process based upon probability of subsequent outcomes that it learns from existing data. By using a collection of the most commonly found vertical slices used in Mario levels, as shown on screen now, the system can then analyse a set of one or more levels, build the Markov model, and then attempt to produce levels with similar properties. As you can see here, the resulting levels not only appear to reflect specific designs from existing Mario levels, but concatenate them in ways not previously considered. Next up, let's swing over to the United States and the work of Adam Summerville, who completed his PhD at UC Santa Cruz in 2018 and is at the time of this video an assistant professor at California State Polytechnic University. Adam has worked on a variety of fun research during his time as a grad student, but he tried out 2 distinct approaches to Mario level generation using machine learning. First up is a project published with Shweta Philip and Michael Mateus in 2015 that shares some similarities with the final project by Dahlskog in that it also uses Markov chains, but tries a different approach at validating the outcome. One element of the n-gram levels that can be problematic is that there's no absolute guarantee that resulting levels are playable. It's at the mercy of the Markov chain producing something that makes sense. Hence, Summerville's paper takes a similar Markov chain approach, but the decisions made by the chain are validated using Monte Carlo tree search, an approach we've previously seen when I explored the strategic diplomacy AI of Total War Rome 2, that checks the decisions being made will not only be playable, but tailors them against specific design parameters. To get started, the Markov chain is generated in a similar manner to Dahlskog's by examining vertical slices of each level, identifying tiles that are either solid or breakable, as well as enemies, pipes, coins, question blocks, and hidden power-ups. Once the Markov chain is established, every step of the level generation process relies on the MCTS algorithm to validate the quality of each possible action that the chain can make. If the Markov chain says there are 3 commonly used follow-ups to the current vertical slice, the MCTS scores them in a number of ways, with the system taking the one deemed most suitable. The MCTS evaluations are multifaceted, given that they're designed not only to ensure that the resulting levels are playable, but also relies on additional metrics that the user can parameterize based on their personal interests. First, each level is assessed for completeness by taking Baumgarten's A-star bot mentioned earlier in this video and using it to test the level. In addition to having the bot test the level, there are independent parameters for desirability of certain level features, such as the number of gaps, enemies, coins, and power-ups. This hand tweaking allows for the designer to have more control of what type of levels are made, all the while relying on MCTS to ensure the resulting levels make sense. The second approach was to use a variant of recurrent artificial neural networks known as a long short-term or LSTM network. LSTM networks date back to the late 1990s and are great for handling sequences of data, given they have a memory component to the input sequence, allowing it to not just read in fresh information, but dictate when to remember or forget data from previous input cycles. As a result, LSTM networks are often used in speech and video recognition processes, given it works well with continuous sequences of data. Summerville attempted this in late 2015 by training a LSTM against 15 levels from the original Super Mario Bros., as well as 24 levels from the Japanese release of Super Mario Bros. 2, often referred to in Western markets as Super Mario Bros. The Lost Levels. Different configurations of networks were experimented with to enable the system to read and generate the corresponding output, with the best configuration, known as snaking path depth, changing direction from up to down then up again when generating levels, but also embed special characters into the generated level that reflect the potential path a player could take, as well as recording the current column it is generating for the level, thus enabling the system to have an understanding of how far into the level it's working. Having trained the snaking path depth network to within a certain level of confidence, it is then tasked with generating new levels as we can see now. These levels are assessed against a variety of metrics. These metrics, as Summerville himself states, are not intended to assess the believability of the level coming from an original Mario game, but instead enabling new levels to be created that share similar properties, but are nonetheless still novel. The evaluation considers not just whether the level is completable, once again using an A-star driven bot, but the percentage of empty spaces in the level, the negative space in the level, which is the empty space the player can actually reach, the number of interesting tiles placed, the number of jumps involved in playing the level optimally, as well as measurements of how linear and lenient the level is to play. The third strand of research to examine is by Matthew Guzdial, who at the time in this video is close to completing his PhD at Georgia Tech University. Matthew's work is arguably the most famous of that discussed in this video, given it's appeared in the likes of Vice, The Verge, Wired, The Register, and New Scientist. One of the big reasons for this is the element of novelty employed in capturing Mario level data. As we've seen already, each researcher is inputting Mario level information in different ways. Dahlskog annotated levels with design patterns, while Summerville fed tile data from levels. But Guzdial's initial work aimed to capture not just level information, but an understanding of how players navigate these levels in real time. So it learns about Mario levels by watching people play them on YouTube. So how does watching a YouTube video result in an AI making Mario levels? As detailed in a 2016 paper co-authored with his supervisor Dr. Mark Riddell, Guzdial's project adopts OpenCV, an open source computer vision toolkit that processes each frame of a given playthrough video. The project aims to achieve two distinct elements. First, determining what can be learned about level layout from scraping video footage, but also then how to represent the design knowledge hidden within the footage such that it can be reproduced for the purposes of a level generator. To learn what it can from the level layout, it runs a process of identifying and categorizing what Guzdial refers to as high interaction areas, a segment of the level in which the player spends more relative time in it compared to others. This can refer to areas with jumping puzzles, floating coins in the map, or question blocks and hidden items such as power-ups. These high interaction areas are identified in the video footage, then analysed to understand how sprites are placed within the sequence. This is more easily achieved in the original Super Mario Bros., given there are only 102 sprites the system needs to consider. Videos are broken up into distinct sections of level by assessing the differences in contents of each frame. The interaction areas that are then found are subsequently clustered such that they can be categorised effectively, resulting in 21 clusters where video segments ranging from 2 to 250 frames in size carry specific interesting properties, such as being underground or up in the treetops. Given that Mario dying, which causes a black screen to appear, would interrupt this analysis process, only video footage where players don't die is used. The second phase is then to build a probabilistic model that's based on the clusters pulled from the video data. This model encodes design rules whereby level nodes, or L in this diagram, can be generated in a variety of different ways due to the data learned from the clusters based on a specific style. This requires the G and D nodes in this diagram to be properly calibrated. The G node of the model represents the geometric information about a given shape in the world that is comprised by one or more sprites. The tree bark and the treetop segments are a common shape that the system recognises and learns to generalise them across a variety of different permutations. But there's also the D node of the model, which stores the relational information of a G node to all other G nodes in a given level. This is essentially encoding design knowledge of how objects are placed relative to one another. So the system has effectively grabbed all this video information, parsed out interesting shapes that use specific sprites, then learned how those shapes relate to each other. The interesting part of this is that it's not learning how to make a Mario level, nor does the system really understand what Mario is. Instead, it's learning how sprites are positioned relative to one another in segments of video footage that just so happens to come from a video game. When the model is ready, it can generate segments of level by considering the shapes that would typically appear in that segment, which in turn need to consider not just the sprites they would draw on screen, but their position and their relationship with other shapes that would also appear at the same time. The resulting levels are astoundingly accurate for a system that's only learning from video footage. This project was but the start of a longer body of research explored in subsequent years about how video footage of games can be harnessed not just to understand how sprites can be put together for level designs, but how it can recreate actual in-game behaviour, such as collisions, jump physics, and scoring mechanisms. Last, but most certainly not least, is more recent research by Dr. Vanessa Volz, a PhD graduate from the Technical University of Dortmund and is at the time of this video a research associate at Queen Mary University in London. Volz's research can be found in a paper published at the 2018 Gecko conference with co-authors Jacob Schrum, Jielin Liu, Simon Lucas, Adam Smith and Sebastian Risi, that explored how to build levels using a process known as Generative Adversarial Networks, or GANs for short. GANs are a process of unsupervised learning that has proven popular since their inception in 2014, but is based on existing research on adversarial learning between neural networks that dates back to the early 1990s. A generative adversarial network is a deep learning technique comprised of two distinct convolutional neural networks, known as the generator and the discriminator. The generator is creating solutions to a given problem, while the discriminator evaluates their quality. To make this happen, the discriminator is learning to recognize a specific set of examples from a dataset, while the generator learns to create samples that fool the discriminator into thinking what it's created is authentic. Over time, each system becomes increasingly better at their respective tasks, with the discriminator becoming better at recognizing authentic data, while the generator becomes better at fooling the discriminator into believing its output is authentic, and, as a bonus, the output of the generator improves in quality. This approach has resulted in significant improvements in fake AI-generated imagery and style transfer of photographs. But arguably the biggest impact it's had on gaming thus far is the recent work in modding communities using machine learning to upscale textures to 4K resolution for games such as Elder Scrolls Morrowind, Doom, Metroid Prime, and Final Fantasy VII, which we could explore as an episode in itself if you're interested. Let me know down in the comments. But bringing it back to Mario, how did Volz and the rest of our fellow authors get this running for Mario levels? To do this, it's broken down into two distinct phases. The first part is training the desired generator network. The discriminator is trained against one level of Super Mario Bros., while the generator is trained to start learning how to fool the discriminator. Once this process is completed, the generator can now create new levels that fool the discriminator, and thus enables the beginning of the second phase of learning. This second phase uses a process known as Covariance Matrix Adaptation Evolutionary Strategy, or CMAES for short, to further train the generator such that it can build levels that reflect specific design properties, such as the number of ground tiles and enemies placed, but is also evaluated based on whether Robin Baumgarten's A-star bot can complete the generated levels and the number of jumps it requires to do so. This ultimately results in levels such as this one here that is based on snippets generated by the system, but ordered in progressively more difficult segments. While it isn't always perfect and requires the encoding used by the system to be properly calibrated, the real benefit of this approach is that levels can be generated very quickly, to the point it could in theory generate new levels for the player while they're in the middle of trying out existing ones. If you're keen on trying out this generator yourself, the code is available up on GitHub, and you can find the link down in the video description. Within the last 7 years, machine learning techniques have been shown not only to provide a viable option for procedurally generating Mario levels, but they're doing so at a level of quality that surpasses much of the existing work in the field. There is great potential for these techniques to be employed in similar 2D tile-based games, but with their own unique level design principles. A level generator that mimics the rules of Mega Man, something that Guzdial's work has already started to replicate. What about expanding this theory out to the Metroidvania genre, where there are rules of interconnectivity and backtracking that need to be considered? Maybe even Legend of Zelda dungeons? Actually, Adam Summerville has already conducted some work in that space, and we could look at that in the future. But beyond that, I have another question. What other kinds of experiences could these generators make using the Mario template to surprise us, to challenge players with something new and exciting? Back in 2016, I presented a paper looking at the most popular levels on the original Super Mario Maker for the Wii U that were hosted on the online service and voted for by the community. What I found was a diverse range of levels that take the basic template of Super Mario Bros. And try some fresh new ideas to innovate on the formula. Referring back to earlier in this video when I mused about what humans do when given their own Mario level creation tools, the results I found were fascinating, with a variety of unique and novel designs that completely break from Mario level design principles. This sense of creativity that transcends its origins represents a new space of possibilities to explore in the future, and it's clear from the ongoing investment in Mario level generation that this is far from a closed chapter in the world of procedural generation research. And funnily enough, just as I was putting the finishing touches to this episode, a new and improved version of the Mario AI framework was made public and ready for a new generation of researchers and hobbyists to use. The framework is being built by Ahmed Khalifa, currently a PhD student at New York University, and seeks to not only integrate many of the original features from the 2009 version, but adds built-in AI players and level generators, contains thousands of generated levels from previous competitions, and aims to better support continuing research in the future. All that, and it's using the original Mario art too. Head on over to marioai.org to learn more and download the latest version. I've also placed the link in the video description, so be sure to go check it out. Thanks for watching this video on AI in games. It's just under 5 years since I published the video on the Mario AI competition, and it's great to get a chance to return to this ever popular corner of academic research. Don't forget to give it a cheeky like and subscribe for new explorations of artificial intelligence in video games each and every month. Special thanks to Steve, Adam and Matthew, who provided me images from their level generators to use in this video, as well as to Vanessa, whose existing video footage was adopted for this episode. This video was voted for by my supporters on Patreon. To have a say in the topics explored in this series and to have your name up on screen right now, head on over to the AI in Games Patreon page via the links on screen now and in the description.